Okay. If you have any question, you can ask. So we will cover today 4.3. That is 4.3 is basically some services of network layer. So we have started with forwarding table, routing table. Yesterday we will continue from here. So 4.3 is about routing or forwarding table, how a router works, and also there are some other concepts like fragmentation and network address translation. So we will cover this part today. So no question from your side. Okay, then I have a question. What are the two main functions in network layer? Tanveer Hassan, can you tell me? Tanveer, what are the two main functions in network layer? Ashrafun Nahar, can you tell me? See, we have discussed in the last class in depth. There are two main functions in network layer. Anybody else? Anybody can tell me?
Sir, it is routing and gateway.
Routing and
Gateway.
no, routing is fine. Another one?
So providing
Right.
IP address.
Providing IP address, sir.
Actually, main functions are routing and forwarding. Providing IP address is actually the part of the responsibilities, because without IP address, network layer cannot uh, identify a particular device in the network. So it is about uh, routing and forwarding, right? In the last class we have discussed, and forwarding is actually based on the path decided in routing. So everything we will work on network layer is definitely based on these two fundamental functions. We have to decide a path. That's why we need to implement the routing function that is global. Why that is global? Because that must incorporate the entire network topology. That is from source to destination. If you start from Dhanmondi, if you want to go to our permanent campus by your own, you must know the options, right? You must know the maps. What are the possible paths you can decide? So if you don't have the knowledge, you cannot decide. So that's why it is global, and the outcome is a path, and every router contains a path and represented by a forwarding table or routing table. And then forwarding is based on the path at each interchange. So interchange in the road is like a router in the network, because router actually receives a packet from an input port and then decides which outgoing port it must forward the packet. Right? Clear? So everything we will use, we will learn in this chapter, we must understand the routing and forwarding concepts. Anybody has any question?
No,
Okay.
sir.
Okay. So one more thing, we will have our in-class assignment 3 in the last class before the break. I could have given this on Wednesday, but I think it would be better to give it on Sunday. Anybody has any problem?
No, sir. Sunday will be okay, sir.
Yeah, because there is a weekend.
Yes, sir.
So I think it will be helpful for you. Also, another thing is the examples I will cover in the class. If you understand the examples, very good, then it will not be a problem in the in-class assignment, as you saw in the last in-class assignment. So it's not a, don't think about too much on this. Just you need to understand the examples I cover in the class, the concepts and the examples. Okay, so you'll have our in-class assignment 3 in the next Sunday.
So what will the syllabus you this year?
Yeah, syllabus will be 4.1 and 4.3. See, I have specified here. So 4.1 is basically the introductory concepts. What is network layer? What is the main functions? As I said, routing and forwarding. So this is 4.1. Actually, every chapter's first section deals with the layering concepts that we have covered in chapter 1. So we just review. And then 4.3 contains this routing and forwarding table. We'll see an example today. And oh, sorry, there is a mistake here. Fragmentation and network address translation. So we will cover the theoretical concepts today, and we will do some hands-on examples in the next class. Okay, so 4.3 will cover this, and the syllabus will be 4.1 and 4.3. Okay, so that is about today's class and the in-class assignment 3. Now let us go to our example where we have finished last class. Let us start from there. Okay, as I said, those who have who are doing computer network lab, it will be very easier for them. But those who are not doing the computer network lab, you have to have some basic knowledge about IP addressing, IP version 4. In IP version 4, let me just give you some basic introduction. So this will be helpful for you, for those who are not doing labs. Okay, so IP version 4. Now IP version 4 is 32 bits number, and this is basically represented as 4 parts, each with 8 bits, right? And then represented as dotted decimal. Okay, so dotted decimal means, like, we can give an example, 192.168.10. maybe 11. So see, there are 4 parts. Each part is represented by 8 bits, and 8 bits that is represented as a decimal. So you have done binary to decimal, decimal to binary in many other cases, like in digital logic design and other courses also. And for IP addressing, you need to just practice a little bit. You might need that, converting decimal to binary and then binary to decimal. And then 4 parts of 8 bits each. Each part with 8 bits. So 8 bits, if we convert 8 bits to decimal, it can be 0 to 255 each part. So there are 4 parts. You can see 1, 2, 3, and then 4. So there will be 4 parts. So 4 into 8, 32 bits. Now, just you have to keep in mind some information. First one is class. So for class information, just I am giving you the basic thing. You have to make sure you understand these basic things. For those who are doing labs, it will not be a problem, but for those who are not doing labs this time, You have to know the basic, not the very detailed one. So there are different classes. If we say class A, class is defined by first 8 bits. Okay, so first 8 bits of each number. So if I say class A, that means first 8 bit converted to decimal will be 1 to 126. So if you see the first 8 bits of a IP address converted to decimal is between 1 to 126, that is class A. Okay, before that, just give you another generalized information. There are exactly 2 parts. If anybody has any confusion, even those who are doing labs, okay, please feel free to ask me. I'm just summarizing the basic things that we need for the concepts in network layer.
Sir, I have a question, sir.
Yes.
স্যার আমাদের কি স্যার পরীক্ষার জন্য কি পুরো রাউটিং টেবিল বা আইপি টেবিলগুলো লিখে লিখে ক্যালকুলেট করে দেখাইতে হবে নাকি শুধু ক্যালকুলেট করলেই হবে আইপি যদি আপনি দেখাইতে বলেন
Actually, I will not ask based on IP addressing calculation, but you might need to show the calculation for routing table purpose.
ওকে স্যার মানে
Let me
বেসিক্যালি স্যার আমরা সিএন ল্যাবে যেটা করতেছি স্যার সেটা হচ্ছে স্যার আমরা একটা আইপি অ্যাড্রেস থেকে সাবনেট মাস্ক ডিফল্ট
Right,
গেটওয়ে
right,
নেটওয়ার্ক লেয়ার নেটওয়ার্ক অ্যাড্রেসটা কি হবে সবকিছু বের করে একটা টেবিলে সাজাইলে সেটা হচ্ছে রাউটিং টেবিল হয়
Right,
বেসিক্যালি
right.
আপনি তো এটাই চাবেন আমাদের
Right. Not more than that, but just for the routing table purpose, you need to show some calculation. That's why it is
Yeah,
not
yes, sir.
like I am asking you the subnetting question. I will ask you
Okay,
the
sir.
routing table question. So for those who are doing labs, I think you are doing labs, so it will not be a problem. But for
Yeah,
some
yes,
of the students who are not doing lab this time, you need to understand the basic concept so that you can relate to the routing table. That's why I am giving you the basic review. So there are exactly 2 parts in each IP address. One is network part and another one is host part. Okay, so whenever you give an IP address, you have definitely you must know what is the network part and what is the host part. Why you need to know that? Okay, I will make sure. So how to identify a class? If you see the number 1 to 126, that means class A. And in class A, one other thing is
So class A থেকে 1 to 7 পর্যন্ত ছিল
but 127 is reserved for loopback. Okay, loopback. So that is actually not included in class A. That is a special IP address. Okay, first 8 bits network. So first 8 bits will represent network in class A. So in class A, first 8 bits are network bits. Then in class B, just let me copy this to make it faster. For class B, 128 to 192. First 16 bits are network bits. This is by default, but we will see this can be changed. This can be changed. So in class C, it will start from 191. Previous one is 191. So 192 to 223. First 24 bits are network bits by default. Now, if we need to know another type, that is network address for routing. Why network address? Because, okay, how we get network address? Set all host bits to 0. So if you set all host bit to 0, for example, if you see one example in the previous case, this is what? Which class? 192.168.10.11, which class?
Class C.
Class C. Because you need to know the first octet only. So the first octet 192 to 223, class C. If it is class C, how many bits network? 24. So that means 8, 8, 16, 8, 24. So this is the network part. So what is the host part? Last one. So this is the idea. So if we set the host part to 0, what will be the network address representing this IP? 192.168.10.0, right? And since there are 24 bits network, we can write like this. /24. /24 means for this address, 24 bits is network. Now you can tell me, okay, we all know for class C, 24 bits are network bits. So why we need to write /24? That is true, but when we actually divide a network into a smaller networks, we can borrow some bits from the host part and then add to the network part to group the hosts. In that case, this number of network bits might increase. Okay, so I am not going to that much details. You have to understand these basic things, but we can represent a network address like this. Now, why we need network address? Because if there are 100 hosts in a particular network, then the router connected to that network must contain in its routing table 100 entries. Like, so if a packet comes with a particular IP address as the destination, it must store that information in its routing table. Now, instead of storing 100 entries for the routing table, because there are 100 hosts in the network, if we have one single address representing the entire network, how many entries we need to store in the routing table?
1, sir.
1. Even if there are not 100, there are 10,000 hosts in the network. How many entries we need in the routing table? 1, right? So that is the advantage of using network address, because network address all host bits 1. Your ID, right? Student ID 011181000. No student has that ID. So I can use that 000 to represent the entire 181 batch. That is the idea. So in networking, especially in routing, this is very important, because my routing table will be smaller, searching will be more efficient if we represent only using one single network address. We can represent the entire group. Okay, so that's why routing table uses network address. How we can get network address? If you can always see, if you give show IP route in the lab, you will always see the routing table, and you will never see an entry that is not network address. So if a packet arrives at the interface, at the port, router has received a packet, and there is a source IP address and there is a destination IP address. Now, that destination IP address is definitely not a network address, right? It is a valid IP. It must be IP address of a particular host, like this, like 192.168.10.11. So what router will do? Router will find the corresponding network address. How? All host bits, set all host bits 0, like this. So definitely, if router knows the destination, router has an entry in the table, so it will just match and then forward the packet to the proper outgoing link. So that is the idea. And that's why we need this basic information for IP addressing to work with routing and forwarding table. Okay, so this is the basic you have to understand. Any question, anybody? Okay, now we will use this information to understand the routing table. As I said in the last class, a routing table contains entries for what? For network address. So how many networks are known here? Anybody can tell me?
4 networks, sir.
4 networks. Actually, out of 4 networks, 3 networks are defined. So if I say one more thing, if I say I got a network address like in the previous one, 192.168.10.0/24, then I can get a range of values that can be assigned to hosts. That means this network represents valid hosts from 1 to
254.
254. So 168.10.1 to 192.168.10.254. Now, why we need this? Because a packet, an arriving packet, will have a destination IP, a valid IP. So if that represents, if that IP is in this network, then can I say that destination IP must fall between this range? Yes or no?
Yes, sir.
Definitely yes. So that's why to understand a routing table, we can think, although routers store network addresses, we can think it as a range of IP. And since IP version 4 address is 32 bits, so we represent in binary here for understanding, but in practice, actually this is represented in dotted decimal, as I have shown you an example, 192.168.10.0. And but all the calculations are done internally in binary. So in this case, you can see the yellow shaded region actually represents the host part. And this is not the case how it practically works. This is only to show that out of these 32 bits, first 21 bits represent network, last 11 bits represents host. So you can see this through this. That means this is the host range. So every network represented by a range, and there is an otherwise, that is the default. That means if none of these 3 entries match, then router will forward to interface 3, because it has been saying otherwise forward to interface 3. But this is not mandatory. The routing table could have a default route or maybe not. So in that case, if none of these entries match, then router will drop the packet. So this is the simple idea. Now let us go to an example. This is actually shown that this range can be divided into sub range. That is actually we call subnetting. When we divide a network into a smaller parts, then the network bits can increase. As I said in the last case, network part can increase. So there can be multiple sub networks under the network. Let us see an example. It will be clear. For example, this is a routing table that is given. Now, what is meant by this don't care star? A star means what? 0 or 1, anything can be here, right? You use this don't care previously.
Yes, sir.
So why this don't care? Very important, because when router matches an entry, it gets how the process starts. It gets a packet with a destination IP. So it needs to decide to which interface this packet should be forwarded, right? How? The idea is it will take the destination IP, it will get the network part. How it will get the network part? For example, it will first match with first entry. So first entry says how many bits in the network part?
21, sir.
So
Very good.
21.
21 bit. If anybody has any question, please, I am taking time. This means 21 bits network, because you see this 21 bits is fixed and the rest are don't care. That means anything can happen, anything can be there, but these 21 bits must match to forward the packet to interface 0. So what router will do, it will take the packet, it will extract the destination IP. That destination IP will be how many bits?
9 bit.
No, how many bits that destination IP will be? Any IP version 4 address is how many
32
bits? 32 bits. 32 bits. So doesn't matter what is in the last 11 bits, right? That first 21 bit must match with the first entry to forward the packet to link interface 0. Suppose first 21 bits doesn't match with this first entry, no problem, then it will search for second one. This is how it works. If, else if, else if, else if, then the last otherwise is like else, similar to that default case. Okay, case 1, case 2, case 3, then default. So first one doesn't match, then it will try for the second one. But see what is here, how many bits in the network in the second entry?
24 bits.
24. So now 21 bits matching will not work. You have to match exactly 24 bits, not even 23. Exactly 24 bits to forward the packet to link interface 1. Suppose this one also didn't match. Then go to the third one. Again for the third one, how many bits must match?
21 bits, sir.
Again, see, so somehow in network, in routing table, if you go again to the routing table, show IP route, you will see definitely there is that /21/24 something there, or subnet mask, to identify this thing, like how
Network
many
bits,
bits
sir.
are right, network bits. So the given network bits in a particular entry must exactly match to forward the packet to that interface. Suppose the third one also did not meet, then go to the fourth one. That is the default. So in this case, anything will match, anything, like our default case 1, case 2, case 3, then the last one, any value will match. So similarly, if none of these three match for a particular packet, then default will must match, then it will go to link interface 3. Is it clear? Any question? Now, two examples. If you understand these two examples, for those who are yet to understand the concept, please try to get one example correct. Okay. The first one, examples means actually there is a packet in the interface of a router. A packet came in the interface of a router, and the packet contains a destination IP address of 32 bits like this. And the router has this routing table, given routing table. Now, which interface it will forward?
Sir,
Zero,
first one
zero,
is 0.
0.
Zero.
Sir, first one.
Right, correct. First one. Okay, how you have found that?
So the if
The
else
third
is
segment 00010 that matches with the first one.
Yes, that means the first 21 bits match, right?
Yes.
So for a routing entry to match, as I said, you must match exactly the number of network bits. So the first entry number of network bits given 21. So what router will do? It will take 21 bits from the first given packet IP, right? Destination IP, and see if it matches. So we can see 1100100000010111 and 00010. So first 21 bit matches with the first entry. So it will not go to the next one. It is if else if, right? So whenever it matches, it will forward the packet to link interface 0. So what will be the result? Interface 0. See how it matches?
Yes, sir.
Anybody has any question? Those who are not doing left, please ask questions if you have any confusion. Otherwise, it will not be easy. Okay. So now, okay, let me start again. Sorry. So the first one, you can see the 21 bits matches. If suppose it did not match, then it will definitely go to the second one. But since the first entry matches, it will send to interface 0. Now, before going to the next one, second example, let me ask you which interface it will forward.
So link interface 1, sir.
1. Okay, but can I say okay, why 1? Because 24 bits match, right? Exactly 24 bits match. But I can see the third entry also matches, but in this case 21. So theoretically, can I say the second example matches with both entries 2 and 3?
Yes, sir.
You can say, sir.
So this can happen, and this is a very important phenomena in routing, especially in internet, when we actually connect to the internet through a ISP, right? So ISP gives us some block. If I change the ISP, then what will happen? So this is a very important phenomena, and theoretically, if multiple entries match for a particular packet, then which interface it will forward? The interface, the entry with which more number of bits match. So you can see, although the second example matches with second entry, 24 bits matches, and for the third entry, 21 bits match here. So both matches, but longest prefix match is a concept that says when looking for forwarding table entry for given destination address, use longest address prefix. What is prefix? Number of network bits. Prefix is slash something, slash 21, slash 24. So this is called prefix. That means number of network bits. So if you have multiple entries match, you will definitely forward the packet to the entry that matches maximum number of bits. So out of this entry 2 and 3, entry 2 has 24 bits match, entry 3 has 21 bits match. That's why it will forward to interface 1. Clear?
So তাহলে কি longest matchটা সবসময় উপরে রাখা উচিত?
Right, good point, very good point. Longest match actually, okay, interesting point. If you see entry 2 and entry 3, is there any relationship of subnetting here? Anybody?
Yes, sir.
Which one is subnet of
Sir,
the other?
3 don't
Second entry is the subnet of third, or third entry is the subnet of second?
Sir,
So there is a confusion, right? But it is very simple. For the third entry, how many host bits?
Sir, 11.
11. For the second entry, how many host bits?
8, sir.
8. So when we subnet, host bits increase or decrease?
Increase.
Decrease, because we borrow host bits from the host part. So from 11 bits, actually 3 bits has been borrowed to create subnet, right?
Okay, sir. Yes, sir.
So which one is subnet of the other?
So 1 is subnet of 2.
Right. Entry 2 is subnet of entry 3. So that is the point. You said the more bits, matching more bits should come before the matching less number of bits entry, right? So in practice, subnets come first. So if subnets come first, then this is always happened, right? Because if subnets come first, then more bits automatically match first. So else if that matches, it will not go to the third entry, definitely. But if it is vice versa, like the second entry is placed in the third position, third entry is placed in the second position, then what will happen? If you think if else if, then whenever it matches to this, it will go to interface 2. It will not check interface 1 if the position is altered, right? But in practice, definitely the entry, if it is a subnet, it comes first before the supernet or the original network. So that's why it always works like longest prefix matching will be matching first. But in the question, I might put entries in the reverse order, because that is not practice, that is for your understanding. Still, I might ask a question. You have to think about longest prefix matching. So whenever there are more entries match, you definitely will go for longest prefix matching. Is it clear?
Yes, sir.
Okay. So like this is matching, but also this is matching, but this matches with more bits. So it will forward the packet to the entry with the more number of bits. Okay, so that is about the routing table. We will do hands-on in the next class. Let us forward our concept to other two theoretical concepts. And before going to the next concept, we have to know about a little bit more about network layer. So as we said, network layer main responsibility is path selection, selecting a route, and the output is a forwarding table or a routing table. And also it uses IP, Internet Protocol, which has a datagram packet format with some header. We'll see the structure of the header. Then it provides us addressing. Which addressing? IP addressing. And then it packet handling conventions. As we said, in forwarding, it receives a packet, it forwards the package to the next node. And also there is another protocol called ICMP. I think many of you doing lab, you have used many times that ping. Ping is a protocol used to verify the connectivity of a destination. So it's called error reporting or signaling protocol. But ping uses ICMP protocol. That is also part of network layer. And as you can see, the upper layer is transport layer, TCP, UDP, and the lower layers are link layer and physical layer. We have already covered this in the chapter 1. Okay. Now, very important, we have to understand the header fields of a IP datagram or packet. So first of all, you can see each row, similar to TCP, each row is 32 bits. That means 4 bytes, right? And you can see 1, 2, 3, 4, 5 fixed header rows. So 5 fixed header rows means how many bytes must be there in the header?
40 bytes.
5,
Sorry,
no,
sir.
5
5 into 32.
5 into 4, right?
Yes.
5 into 4, 4 in each row, and we can see top 5 rows are masked. That is 5 into 4, 20 bytes, similar to TCP. Similar to TCP. And there is one other optional, if I want, I can use, that is 4 bytes. So minimum header is again for network layer is 20 bytes. So if any question, if anywhere you do not find the header size, you can safely assume that is 20 bytes. If it is not said in the question, you can assume it is 20 bytes. But it can be 24 bytes if we use the optional field. Okay. And the data here is what? A TCP or a UDP segment, right? Because it carries transport layer data. Now, let us understand the header fields. Source IP address, destination IP address, very clear. Source IP and destination IP. So we have 3 more rows. In the first row, the first one is version number, like IP protocol version number, IP version 4. Okay. Then there is a header length. As I said, it can be 20, it can be 24. So header length. Then there is a type of service. Type of services it can differentiate like video, audio, and different flow of data, flow of packets. Length is the total length of the packet including header and data. Then maximum length of a packet can be 64 kilobytes, but it can be 1500 bytes or less also, but maximum can be 64 kilobytes. Then you can see type of service. As we say, there are different type of service. We are not worried about that. Don't worry about this deep servant ECN. But we need to understand time to live, TTL. TTL is remaining maximum hops. So it will just indicate how many hops remaining before the packet will be discarded. This is a mechanism to discard a packet so that packets will not travel the internet for infinite time. So protocol set this value, and when this value becomes 0, every router will decrement this value before forwarding, and when this value becomes 0, then that router will not forward the packet. So this is a mechanism to discard a packet. For many reasons, packet can just go here and there, and it can create a looping. Okay. Then upper layer protocol can be TCP or UDP. Okay. And there is a header. Okay, there is a header checksum that is used for algorithm for checking the error. So if there is an error, then it will be discarded. If there is no error, then it will be accepting and presenting to the transport plan. And the last one is the second row. You can see there are 3 fields, 16-bit identifier, that is ID. Then there is a flag. Any question? There is a number of flags, and also there is an offset. We will see shortly how these 3 fields are used for a concept called fragmentation. So that is the outline of IP datagram format. Any question, anybody? Sorry? Okay. So you can see overhead 20 bytes was at TCP, similarly 20 bytes of IP. So it will be added in the network layer with application layer header plus TCP header plus IP header. Okay, before going to network address translation, let me first cover the fragmentation, because we have seen there are 3 fields in the header: ID, flags, and offset, that represents a fragmentation reassembly. Now, why fragmentation is needed? See, network layer creates a path between source to destination. So there can be different number of links in the middle, and each link is actually defined by a particular data link layer protocol. And we can see links can be wired, links can be wireless. Even wired, wireless have different types of properties like optical fiber or UTP, or it can be wireless like Wi-Fi or cellular. So different type of links has different capacity. Capacity in terms of size of a packet that it can carry. That is called MTU, maximum transferable size, largest possible link level frame. So definitely that is defined by the data link layer protocol, and we are now at the network layer. So network layer has no idea about the link, but when the network layer wants to forward the packet to the data link layer, then data link layer will say, okay, see, my MTU is 1500. You cannot send more than this in size. So if a packet is 4000 bytes, data link layer or link has MTU of 1500 bytes, then it cannot carry 4000 bytes, right? What is the solution? The solution is fragmentation. So network layer will fragment the packets according to the MTU so that each packet will not carry more than 1500 bytes. Okay, so that is called fragmentation. And since there are many links in the middle, the source node will not be aware of that. So it will create a packet maybe of 4000 bytes. But if it goes to a link with lesser MTU, fragmentation must be done. So when we do fragmentation, it will work like this. A large packet, the next link doesn't support the size, MTU is less, so it will divide into smaller datagrams. Still those are datagrams, but how many? These are called fragments. How many fragments we don't know. It depends on the original packet size. But what is important, those fragments must be reassembled at the receiving end to produce the original packet. Clear? So
Yes, sir.
whenever it is divided into fragments, it must be reassembled only at the receiver. Now, how this is done? As we said, there are three specific fields. You can see in this example, one is ID, one is flag. There are many flags, but we will use one particular bit of the flag, and there is an offset. So if a router receives a packet that is not fragmented, that is the original packet, but when it wants to forward, the next link says, okay, I cannot carry more than 1500 bytes in a single packet. That is represented by MTU, right? So suppose we have a packet with 4000 bytes original packet, and the next link has MTU. Now router must fragment the packet. How router will fragment? First thing, it will use ID. So what is the ID of the original packet? X, right? Given. Whenever a packet is generated that produces an ID, whenever that from the source, so that ID will remain same. Now this is important. When router fragments this original packet into a number of fragments, that actually will keep the ID same. First thing, so ID will be same for all the fragments. What is the advantage? There can be multiple packets fragmented, right? Multiple original packets fragmented, and one packet has 3 fragments, one packet has 5 fragments, and all these 3 plus 5, 8 fragments, each one is a separate datagram or packet. So whenever it reached at the destination, it can be like out of order. So 8 fragments received, but which one represents to packet 1, which ones represent to packet 2, receiver must identify first, right? Clear? So this is the reason why the original packet's ID will be kept same for all the fragments. First one. Second one, if the router fragments, it creates 3 fragments, it must create in such a way so that the last fragment has some sign. Why? Because after receiver receives the last fragment, now it can start reassembly. So how receiver will know this is the last fragment? Sender must create the fragments in a way so that receiver will know, okay, I have received all the fragments, including the last one. So that is the fragment flag. So fragment flag is 1 when that is not the last fragment. For the last fragment, fragment flag is 0. I'm going to the example, just a minute. And the offset, even if I set the fragments correctly, maybe the second fragment comes before the first one, maybe the third one comes before the second one, right? It can be out of order. So the receiver knows, okay, I have received all the fragments, I have received the last fragment, but I have to order the fragments in correct order, right? How? That is the offset. So every fragment will have an offset, and offset is actually cumulative. So even if the third fragment comes before the second one, if it's sorts according to the offset, it will get the correct order. Logic clear?
Yes, sir.
These 3 fields are used for reassembling. Now we'll see in the example how this is done. But before going to the example again, see, fragment flag is 0 and offset is 0. So flag is 0 for the last fragment, right? And offset is 0 for the first fragment. Always make it clear. Offset is 0 for the first fragment, and the next fragments will generate an offset based on the data sent in the first fragment. third fragment will generate an offset based on the data sent in the first and second fragment. So it's cumulative always. So the first fragment has offset 0 and the last fragment has flag 0. So if we have both 0, what that means?
New packet is not fragmented.
Very good. Packet is not fragmented. So if you see flag is 0, offset is 0, that is not fragmented. So our original packet will have definitely both 0. But since the MTU is 1500, we have to convert this length into individual packets with length 1500. Now keep one thing clear. What is the header size? IP header
20
size.
bytes.
20 bytes. Since this is not given here, we'll assume it 20 bytes. So one more thing, 4000 byte datagram has 20 bytes header, and when you fragment, every fragment will have total length 1500 including the header 20 bytes. So every fragment will be a packet also with individual headers. So if I create 3 fragments, each one of these fragments will have its own header. So in fact, we can transfer 1500 minus 20, that is 1480 data in each fragment.
Okay,
Now
sir.
come to the solution. I have given you the logic. Now if I see the solution, it should be clear. See, these 3 are fragments. How can you understand these are fragments? Because none of these has both 0. Flag or offset, both 0. Only original has both 0. That means not fragmented. But each one has at least one non-zero. That means all of these are fragments. Okay, how these fragments is done? ID is kept as the original one. Original packet has X, so every fragment has X. Very simple. 3 fragments created. Why 3 fragments? We'll see. But the first 2 fragments, fragment flag 1, because this is not the last fragment. Only for the last fragment, fragment flag is 0. For the first fragment, offset is 0. For the second fragment, offset is actually data sent in the first fragment. Why that is 185? Let me clear. And for the third fragment, actually, the offset will be data sent in the first 2 fragments. So if it is same amount of data, see, the third fragment will be the offset will be the double of second one. Why? First one, 1480 bytes in data field. Why? Because length is 1500, MTU is 1500. That means we can send only 1480 bytes of data. So if I want to calculate what is the data size, this is called payload or data. This is excluding header. So subtract 20 from 4000, you will get 3980 bytes, right? This is the data portion that must be accommodated in the fragments data portion. So the first fragment carries 1480 bytes of data. Still you have 3980 minus 1480, right? Then the second fragment again carries 1480 bytes of data. Another thing is how offset is 185. As I said, the offset in the second field will be the data sent in the first field, first fragment. How much data sent in the first fragment? 1480, right? And then there is a tradition, that is you have to rule. This is a rule. You have to divide it by 8. So 1480 is the data sent in the first fragment. Divided by 8. This is, you can find, this is 185. So offset is 185. Why divided by 8? Just to store larger value, nothing else. Just to store a larger value, because number of bits are fixed. Yes, question?
অফসেট স্যার 1480 যেটা এটাকে 8 দিয়ে ভাগ যেটা করছি সেটাকে আমরা বিট আকারে লিখছি কি?
Sorry?
1480 কে যখন আমরা 8 দিয়ে ভাগ করতেছি অফসেটটা,
Right.
সেটাকে আমরা কি স্যার বিট হিসেবে নিচ্ছি? অফসেট
No bit. It's not bit. It's a value. Simply, it's a value. Why it's a value? See, it doesn't matter what is the unit.
অল
Because
টাইমে
for
কি 8 দিয়ে ভাগ
Right,
করব?
right. All time you have to divide by 8. For example, for the third one, it is not shown here, but it is shown in the book, textbook. You can see the textbook. For the third one, what will be the offset? 1480 plus 1480 by 8, right? right? Because first and second field, please mute your microphone, please. For the third one, first two has sent 1480 bytes each. So what will be the offset for the first one? Data sent in the first two fragments. So 1480 plus 1480 divided by 8, you will find 370. Now, if you add 1480 with 1480, and if you subtract the original data of 3980 of the original packet, you will find only 1020 bytes remaining. So the third fragment will contain 1020 bytes, but header is 20 bytes, so it will be 1040 bytes, and this will be the last because it is less than 1480. So this fragment will be the last, so that's why we set fragment flag 0 and offset 370. Now, what happens if number 3 fragment comes before the number 2? No problem. Receiver will sort according to offset. Right? So this is the logic. Even if a fragment is lost, the second fragment is lost, when receiver sorts, receiver will see, okay, my first fragment is 0, second fragment offset is 370. It cannot be true, because first fragment has data 1480, so it must be 185, but I did not receive any fragment with 185. It is 370. That means a fragment in the middle is lost. Is it clear? So in that case, receiver will understand that a fragment is not available, and it will wait for some time. After the timeout, it will discard all the fragments because it did not receive all the fragments. So this is the idea. So this is fragmentation and reassembly. Any question? So we'll use the three fields to do fragmentation and reassembly. So we cannot start network address translation today. I think we will start. We'll complete NAT tomorrow, and then we will go to next topic. But your in-class assignment will be based on up to NAT. So NAT will be included in the in-class assignment. Okay, let me take the attendance before you leave. Please respond quickly, okay? So today is 0521. Abdullah Al Rifat.
Yes, sir.
Enamul Haq.
Present, sir.
Okay. Imam Reza. Imam Reza. Rokunuzzaman Khan.
Sir, Imam Reza texted in the chat
Message
box.
box? Okay.
Yes, sir.
Okay. Rokunuzzaman?
Yes, sir.
Okay. Laila Ishrat?
Yes, sir.
Farah Farzana? Fazle Rabbi?
Yes, sir.
Priyabrato?
Yes, sir.
Ifat Rahsan?
Yes, sir.
Ali Ahmed?
Yes, sir.
Kaushik?
Yes, sir.
Khurshida Jahan?
Present, sir.
Samir Ahmed? Mahmudul Hassan? Fahim Shakil? Abu Sajjad?
Present, sir.
Nibiruzzaman? Sadman Sakib?
Yes, sir.
Adnan Kobir?
Yes, sir.
Taki Yasir?
Present, sir.
Shahadat Hussain? Rakibul Islam?
Yes, sir.
Al Shahriar? Tanvir Hassan?
Yes, sir.
Sakib Hussain?
Yes, sir.
Mashuke Alam?
Yes, sir.
Sabbish Sharkar?
Yes, sir.
Abra Sadiq?
Yes, sir.
Ishtiaq Ahmed? Mufail Abdullah Al Mufail?
Yes, sir. Yes, sir.
Okay. Mahfuzur Rahman Sifat?
স্যার ছিল স্যার
Chilo. Okay. Shafiqul Islam?
Yes, sir.
Amanta Hussain?
Yes, sir.
Okay. Abir Reza?
Present, sir.
Jahidul Islam?
Yes, sir.
Okay. Khalid Ridwan?
Yes, sir.
Okay. Shahriyaz?
Present, sir.
Tahmina Tanjin. Tahmina. Okay. Mohammad Mahfuzur Rahman.
Present, sir.
Yes, sir.
Okay, Tahmina present. Mahfuzur Rahman present. Fazila Nobi.
Present, sir.
Ashrafun Nahar.
Present, sir.
Shifa Chaudhuri.
Yes, sir.
Mesbahul Alam. Mesbahul Alam. Yasir Arafat.
Present, sir.
Sudeep Sarkar.
Present, sir.
Abdur Rahim.
Yes, sir.
Miraj Farooq.
Yes, sir.
Abu Abdullah. Khondokar Shravan. Oh, Abu Abdullah present. Okay. Khondokar Shravan. Shah Alam.
Yes, sir.
Imtiaz Hussain.
Present, sir.
Rifaz Nahian.
Yes, sir.
Amrul Islam Tushar. Dihan Pathan.
Present, sir.
Okay. Abu Kibriya.
Yes, sir.
Bidhan.
Yes, sir.
Shakhawat Hussain.
Present, sir.
Okay. Okay, thank you very much. See you in the next class.
ওকে স্যার, আসসালামু আলাইকুম।
Assalamu alaikum.
Wa alaikum assalam.